Hi there, you're welcome to David's Medical Casebook. Today we are learning about what actually happens to the body after clinical death. Watch and listen to learn.
At 2:14 a.m., the heart stops beating, the monitor flattens into a straight line, and the room becomes unnaturally quiet. A nurse checks for a pulse. There isn't one. The patient is no longer breathing on his own. Within seconds, the body begins to change. Not dramatically, not visibly, but at a microscopic level that medicine understands well. Clinical death is declared when three things occur. The heart stops, breathing stops, and brainstem reflexes disappear. This declaration does not mean the body is immediately beyond recovery. It means the body is no longer sustaining itself. In medicine, this distinction matters because clinical death is sometimes reversible. Within 10 to 15 seconds of cardiac arrest, blood flow to the brain falls to zero. Consciousness is lost almost instantly. The brain, which depends entirely on a constant supply of oxygen and glucose, enters an emergency state. Electrical activity slows, not because the brain is dead, but because it is conserving what little energy remains. This is the first misunderstanding about death. It is not a single moment. It is a transition. In these early seconds, the brain is still alive, but vulnerable. What happens next depends on time, temperature, and whether circulation can be restored before damage becomes permanent. Between the first minute and the third minute after clinical death, the brain undergoes rapid chemical changes. Oxygen levels plummet, carbon dioxide rises, cells switch from efficient energy production to a chaotic emergency process that produces acid and cellular stress. Neurons begin to swell as protective mechanisms fail. Yet during this same window, something unexpected has been observed. In monitored patients, researchers have recorded brief surges of organized brain activity after the heart stops. These are not random electrical flickers. In some cases, they resemble patterns normally associated with memory or conscious processing. Medicine does not fully understand why this happens. One theory suggests it is a final coordinated response as inhibitory systems collapse. Another proposes it is a survival mechanism triggered by oxygen deprivation. What matters clinically is this: the brain does not always shut down immediately or cleanly. By the 3-minute mark, the risk of permanent injury rises sharply. By 5 minutes, many neurons begin crossing a threshold beyond which recovery becomes unlikely. Still, this timeline is not absolute. Some brains tolerate longer interruptions, while others suffer irreversible damage much sooner. The difference is not always predictable. If circulation is restored quickly enough, the heart may begin beating again. But survival does not mean safety. When oxygenated blood returns to starved tissue, it can trigger inflammation and delayed cell death. This process, called reperfusion injury, is why some patients worsen hours or days after resuscitation. In rare cases, something even stranger occurs. A patient is declared dead. Resuscitation stops, and then minutes later, the heart restarts on its own. This phenomenon, known as autoresuscitation or the Lazarus phenomenon, is poorly understood and deeply unsettling for clinicians. There is no single explanation that accounts for every case. Temperature plays a critical role in survival. In cold environments, the brain's metabolic demands slow dramatically. Patients submerged in icy water have survived without a heartbeat for extended periods and recovered with minimal brain damage. This observation led to the medical use of therapeutic hypothermia after cardiac arrest. These cases challenge the idea that death follows a fixed schedule. They show that biology is more flexible and more fragile than textbooks suggest. If circulation is not restored, clinical death progresses to biological death. At this stage, cells rupture, neurons disintegrate, and brain tissue undergoes irreversible destruction. No medical intervention can reverse this process once it is complete. There is no precise moment when this transition occurs. It depends on temperature, cause of arrest, underlying health, and chance. This uncertainty is why medicine approaches death with caution, waiting, observation, and confirmation. What medicine understands well are the mechanisms: oxygen deprivation, energy failure, inflammation, and cellular collapse. What it does not fully understand is why some brains remain organized longer than expected, or why recovery varies so widely between patients. Clinical death exists at the boundary of what medicine can reverse. It is not mystical and it is not instantaneous. It is a narrow window where the body may still return or quietly cross a point from which it cannot. This is not a story about what comes after death. It is a story about what happens inside the body when life is briefly lost and sometimes found again.